Hi, I'm Darrell Aucoin. I'm going to do an introduction on Hadoop talk for Stats Club. Let's get started. Why do we need Hadoop when we have SQL, which is actually a really good database language? Well, our capacity is for SQL is not linear, so you can't. It's really hard to do it in distributed sense. So you can't just handle more and more data just by increasing number of nodes, number of computers you're working on a project with SQL by itself. Hard drives have increased dramatically in capacity, but haven't increased too much on speed. So that means that we store a lot of information, but we can't really access it as fast. Hence the reason why Hadoop is done up. Processing power is bottlenecked. So, like if we can parallelize tasks, what Hadoop basically is constructed around, that helps us out quite a bit. And yeah, as I said, SQL doesn't scale very well. SQL is basically good for gigabytes and so, but after you go into terabytes or petabytes of data, you need Hadoop. But SQL skills is still useful because there's many projects that based off of SQL that, so you could use your SQL programming knowledge to actually work on Hadoop, and it translates everything into Mapreduce kind of cycles. So who uses it? As you see, quite a few, from Amazon to Google to. Yeah, there's many. So why learn it? Well, according to O'Reilly Science Data Survey, it's one of the most correlated factors for high salaries in data science. Highest being when they know Hadoop and SQL at the same time. So let's compare Hadoop and SQL. SQL, gigabytes, Hadoop, petabytes. One of the main things is for SQL, you could read and write as many times as you want. However, Hadoop, you only could write once. So you basically just store data. It's done up so that to maximize throughput, not individual queries. So sometimes it could like a Hadoop Mapreduce job can take an hour or so. So the structure, SQL is highly structured, while Hadoop, it just strings based data, so it could be semi-structured data, so you just have to know, okay, in this instance, we go into this direction. Which also means that SQL is much more integral. You have much more integrity. You have much more consistency to your data. Unfortunately, the only really big downside for SQL is nonlinear. And when going from that's a big cutoff there. So going from SQL to Hadoop, the biggest trade-off is the guarantee of autonomy, consistency, which is basically all what SQL is based around. So write-on schema, basically that's what SQL does. It basically transforms the input into the schema that's already specified in the database. However, for Hadoop, it uses a read-on schema, which brings a file without any kind of gatekeeping, so that it could, if it's badly formatted, you could get a lot of problems, and if it's corrupted, you have to deal with sometimes that within code, and it gets problematic. So, like if one part of the file, if one piece of the data you want is not arranged in the exact same way as the other piece, you have to account for that, and it gets tricky that way. So Hadoop, what is it? It's a MapReduce framework built up on top of a distributed file system. So basically, for this here, think of we have several nodes, which is like computers, like regular just computers, and on top of that, and interconnected to everything is Hadoop. So that basically is both the communications between the nodes and also like what's installed onto it. So, and on top of that is like projects like Pig, Hive, etc. There's basically two versions of Hadoop, 1.x and 2.x. You basically, the main version is there's some limiting factors to 1.0, hence the reason why they had to basically rehaul it. And also, one of the big differences for Hadoop streaming, you could actually stream binary data instead of basically taking it from binary data, convert it to text, then converting the text back to binary data to work on. So it's a little more efficient that way. The main thing we're using for because streaming is on Hadoop streaming, because that's the one that R can interface with, and that's one we know most of. Otherwise, you would have to use either C++ or Java, which limits amount of, like how easy you do queries. So what is Mapreduce? Mapreduce is a programming paradigm where basically to parallelize data, it's composed of basically two main functions, map and reduce. Map filters out and sorts data. Reduce aggregates data according to keys. You basically, for most of the time, you have your base. You try to reduce the dimensionality of your input data, because otherwise, how are you going to get the results back onto your machine? It's kind of difficult. So you can just do map though, like that is a possibility. So sometimes that happens. There's many components. For instance, job tracker, and task tracker. That's basically, think of this just in the background. So this basically incorporates jobs and tasks. Task tracker runs the individual tasks, so each node can have multiple tasks running at the same time. Yeah, if one task fails, it's just rescheduled on another task tracker. If it keeps on failing, then it sometimes just supports the job, depending on the programmer preference, design specs. 2.0 is, well, Hadoop 2 has a lot more, well, basically various components. This is basically more generalized functions, and this helps out a bit more. Resource basically checks the resources. Applications basically just you just do that. Does the application just manages applications, MR for applications. Node managers. 2.0 uses an interface called Yarn, which basically yet another resource negotiator, basically keeping everything up together. This is basically constructs the JVM, Java virtual machines. Hadoop is all written in Java, so it all produces everything in Java, well, with some bash commands as well. So yeah, oversees. So this node manager basically oversees the construction of the JVM, deconstructing it, and running the task. So what's HDFS? Hadoop file distributed file system, fault tolerant, distributed scalar file system across multiple interconnected nodes. Fault tolerant means that if a single node fails, then it won't hop operations. It keeps on going, because if you have tons of computers linked up together, there's a really good chance that something's going to fail. Something's going to happen. So it has to be redundancy built into the system. Yeah, distributed basically means that there's data shared between several nodes. So like one file could be actually on every node in the computer, just different parts of that file. So like the first 64 megabytes could be on the first node, and the next part of it is on like node 5. Because of its fault tolerance, it actually has usually has a replication factor of 3. So each little part is on 3 different machines. Usually like 2 in one rack on 2 different nodes, and another one on a different rack, so that even if a rack goes down, your data's still there. Scalable means that if we want to increase performance, what we just do is just add another node. Keep on adding nodes until you get the power you want, get the capacity that you want. HDFS has various components. Name node, this is kind of like the master node. This manages the blocks on each data node, and it keeps track of where everything is. This is like really integral, and this is also one of the main components for the Hadoop 1.0 being such a limiting factor, because it keeps all of this file information in memory. And yeah, you have to be really concerned of having if you have too much in too many files, like little tiny files, that clogs up the name node, because it has to keep track of each individual file. So that's the reason why you want to have really big files instead of tons of small little files. Data node basically stores the actual data, the blocks. And secondary name node, this is basically just a record keeper of the name node in case something happens and the name node fails. This basically helps recover some of the data that was operating on. It isn't fully. There is a bit of lag there, so it isn't full. If your name node does go down, you do lose data. So it just basically restarts it from the last checkpoint. One of the nice things for 2.0, if a name node goes down, it takes about a couple minutes for it to come back up, new name node to come back up with some data loss. But if it was in Hadoop 1, it was actually around 30 minutes to recover. So built up on top of Hadoop, there's various different projects. Like Hive basically makes SQL-like queries and converting into Mapreduce jobs so it feels like you're running SQL statements. Pig has something very similar, but it uses pipelines, so it makes it look a little more declarative. But it only executes everything when you basically do the commit statement and does relational algebra to find out the easiest way, the cheapest way of doing up the whole job. Yeah, this also has a part to data food, which has a lot of data functions inside of it, which is really helpful. Spark is something fairly new, but also really really popular right now. It's basically another implementation of Mapreduce that's really good for iterative algorithms. So like machine learning or anything like that. So it makes jobs that usually take probably an hour regularly take about a minute or even 30 seconds or so. It also has like Spark SQL and machine learning built into it. So HBase is a very low latency way of looking up tables in Hadoop. And the thing is, you can also do updates and deletes, but you can't join, can't do it isn't as flexible as Hive, but it's a lot lower latency. And Uzi is a workflow paradigm. This basically you could strings up many different projects up together into one job, so you mix and match tools up together. It's Avro is basically for encoding the schema. So like you could basically predefine, okay, this is all this data is in this kind of format, so that way you don't have to always update. Okay, the first one's an int, the second one's a string, etc., etc. You could basically just do it up there. Don't have to worry as much. Macout is basically a data mining library. Scoop basically takes data from SQL and dumps it into Hadoop. So, for instance, many companies have operational data that's stored for quick access, like to basically run the essential business on SQL. Then after a month or so, dump it onto Hadoop and start off a new one, so that it basically you keep a record to do analysis on that, but at the same time you have something to basically process and very quickly run things. He's catalog, metadata management, basically unifies all the data. Mapreduce comes up into several different steps. Record reader, mapping, then sometimes combiner. Combiner usually optimizes how it runs, so it takes less time, and it just I'll show you later. It's going to come up later on, but it helps out the whole job run faster. Partitioner breaks things apart. Shuffle basically shuffles it up for a reduce job, then put up to a reducer. So record reader basically translates translate input into records to be processed by the user. So for an input split, which usually is around 64 megs, or it'd be 128 megs or something like that. So for each input split, it has a mapper task associated with it, and for every record, it puts in a key and value. A key, usually the key is a data number. It's the number of bytes from where the start of the file is, and the value is basically what that record is. So it basically reads off from the input split each new record and puts it through the mapper. Then the map phase, this is what's usually defined by the user. Takes all the intermediate keys and processes it to make up an intermediate value key pair for the reducers. The combiner basically puts it, aggregates the data. It's much like the reducer, but it runs on the mapper job. So you could basically reduce dimensionalities on the node that you're working on, so it doesn't have to send traffic around just to aggregate data by itself. This helps out network sending. So it really, which is one of the big bottlenecks for Hadoop, is basically just sending information all around to other nodes. So combiners help reduce the data size of those packets, so that makes it a lot faster. You can basically think of this for this. So if we're every key, like say the key here is hello world, and we have a value of 1. When the combiner comes up together, it brings up, and say we want to do a sum of those values, it just sums it up to one key value and the sum of all the values here. Usually combiners should be written up in the same intermediate key value split, so it should have the same data type as what you should be sending. You don't want to. You should write up a combiner code so that does not necessarily have to run. Like, it runs usually, but if the data is small enough, it doesn't usually run, doesn't run the combiner. So when you write up combiner code, think very much like a reducer. As I said, very similar, or even the same code as a reducer code. Partitioner breaks up the data into intermediate value pairs. So basically, it chooses the reducer based off the hash of a hash function mod R. What this does, basically, it sort of randomizes everything, like, but at the same time keeps all the keys in the same, sends all the keys to the same reducer. So, like, if there's a value key here, the reducer it sends to is based off hash function, was sort of like a random variable, but not quite. Like each input, each key gives the exact same hash value, and from there it basically puts it up. You could actually write up your own partitioner as well, but you have to do it up in Java, which I don't really want to get into. But yeah, then basically shuffle and sort. It sorts it all by key values to help sum up the values grouped by keys. It does this all up on the reducer node. And then reducer function happens. This is also a user-defined function that aggregates the data according to your keys. And then sends key value pairs to the output. Then lastly, we output the values we want. So the value key pair that we wanted out, we basically send off to HTTPS, and then it does the whole replication factor thing, so it's like a regular file on HDFS. So, like for instance, go through this here. We have various different words here. Think of the input split as actually just a single line this time instead of data size. So if it sends, so each one here, so it's split off into lines. Think of that as just files, file size, and then for mapping, basically it takes each word and gives it a value of 1, and then it shuffles it out so that it partitions the data out to so all cars go into one node, all deers go into another node, river, etc. Then reduces it, so aggravates the 1, and the 3 ones here to 3, and then it brings it all up together. When you do a reducer job, each reducer sends off its own little file, so this could almost think of like partition off like here, but you get that base idea. So HDF operations, a distributed file system designed to store huge streaming files. So it has to be, for instance, you don't want to work on a LaTeX file because there's the header part which the details all the information. LaTeX would not be a stream file. Count separated values is a stream file. Tab separated values is a stream file. So it has to know the data could be. It doesn't matter where you started the data. You know what it is right from that. Yep.
Is that because like a streamable file you could change, like you could be adding stuff to it?
No, the reason why that is because like for the input split, it's separated up by megabytes. Like so, first 64 megabytes is on one node, the second one another. If it had to look up for the first one, it had to basically ask the first node, okay, what's this information? And it gets really complicated.
If it got like split like halfway through the formatting or something.
Yeah, you would basically would have to, it's split up just exactly on 64 megabytes. So so it basically once it's 64 megabytes, okay, second new node. And if you didn't have a streaming, you would basically would have to keep on asking, oh, what's this information? What's this? And it just clogs up the system. And also, how would you know that you needed that information? Where would it know where that information is? It gets really complicated.
Cool.
Distributed file system, so like tons of nodes linked up together. So this allows files to be partitioned, usually according to megabyte size. Well, actually, it always did. Yeah. Usually around default is 64 megabytes, but usually quite a few companies change it up to 128 or 256. Yeah, it all depends on what you want, like how the administrator basically feels. Okay, this is the best file size. Community hardware. Basically, this is just the hardware is good, but it's something that you can buy in your local shop. You don't have to be like super reliant. It doesn't have to be as unbreakable as an enterprise machine usually has to be. So if a node goes down, go down to your local computer shop. You can buy a new node. That's huge files. This basically we want really huge files on it. So at least usually you want at least 100 megabytes to even petabytes of data. Streaming, our documents have to be be able to be streamed because it needs to be partitioned off and read independently. If it wasn't, then we have to keep on figuring things out, which it gets really complicated and much more problematic. HDFS is not very good for low latency. It's designed around throughput, so doing a quick query, it's not going to take. It's not going to be really fast. Hadoop is actually really slow, and that's one reason why they get Spark and other systems to basically go around with that and increase the time to do up jobs. Sometimes it takes about a minute instead of an hour, but even so. Lots of little small files. As the number of files increase, the amount of memory that node has to keep in memory to keep track of everything increases. And if it gets too big, if it's getting outside its RAM limit, then it just crash, and that's all you can do. So when you put a file up on Hadoop, try to concatenate as much as you can. Sometimes you could even zip up a file and into a streamable zip file. That way you could do it that way too. Hadoop also has tons of codecs to zip. Just have to remember to make sure to zip it up in a streamable format so that it can be read independently. Arbitrary file modifications, so you can't change like halfway in through because that might increase the soft file size, in which case 64 megabytes and plus 1 byte, and translate that byte to the next node, and yeah, it gets really problematic. Yeah, the only way you could actually change it is at the very end of the file. I mean, like the very last of the block. So HDFS blocks is basically how data is stored. It's stored up by chunks, 64 megabytes by default, but it can be much bigger. And these are stored across various different nodes. As you basically increase the power of your individual nodes, sometimes it's better to increase the block size because that you can process blocks easier. HDFS blocks are best utilized by evenly distributing large cluster. There's actually programs within it to help balance it out. There's actually a thing called a balancer that tries to do this, but sometimes you have to just basically tell it to balance things out. Block size is balance of production of head seeks on disk and RAM usage. A very small file with like, for instance, a 32 megabyte file on 64 blocks. That doesn't use up the whole block size. So it's just store. The block is stored continuously. Like there, you know how when you defrag, it joins up all your files into one single section. This automatically happens for Hadoop. It has to store it all up on a continuous block, so that way reduce all the head seeks, because head seeks is really problematic, and it gets is a really limiting factor. So that's the reason for that. But if you have less than that, it doesn't take up that full size. It just has that. It only uses up the amount that it has there. Yeah, there's also various commands like fsck, which uses to work on blocks. Like say if a block's corrupted, you actually take the block back and see what's happening and figure it out. HDFS federation is basically a way of for Hadoop 2 to have multiple name nodes. This is basically how and gets around the name node limiting factor. So you can actually have several different name nodes at the same time. Each name node basically handles one part of the file system. So like one name node could handle all the files for this half class. Then another name node handles the file systems for files for this rest of this class. So yeah, they're independent. So if one name node fails, the others will still work. Balancer, this basically helps distribute the blocks roughly evenly across the cluster. Yeah, it tries to keep one replica on one node and one node that's right in the block, and then each node that's then replicated on one extra node on that rack, and then another one on a different rack. So that way, if one rack goes down, you can still have your data. Failure recovery. So go into this so that you know how, if something fails, like how it could fail. It's built into Hadoop. So for instance, if an exception is thrown, you fail a task, then it just basically comes back and tries it again, sometimes on a different node. Name node, a node running in memory or a task can be operating too long without a status update. After 10 minutes, it thinks that, okay, this task is dead. It's just spinning its wheels and just kills the job. Well, kills that task, and then tries it again on a different, either same node again, or sometimes on a different node. Name node failing, that's the really worst one. This is the critical one, but since it's usually only one part, this is not so bad. Task is failing, so like say if this exception is thrown, if it's not handling code, then the task fails. If by default, if it fails, then it tries rerunning on the same node again. If it fails again, then it tries one more last time on a different node. So it tries ultimately 3 times, and if after that its job fails, you can actually change this in parameters. This is one reason why you want to handle things in code. So if something happens, you could actually describe what you need to do and basically either ignore this failure, ignore this block, and just continue on, or whatever you want. So like we could read a corrupt block, and we could handle it in code, catch exception. Bad record could be skipped by enabling this class, skip bad records. This basically so that if it finds a single point, when running through once, it finds the corrupt part here on line 55, and next time around it actually knows, okay, line 55, 55 is bad, so continue on with the next one. This is also a way of also orienting around, so check and see if there's a bad. But if there's if it happens again, then that's considered a failing 3 times and kills the job. So you can also have bad formatting of files. So usually you want to correct formatting, ensure the correct formatting of the file, and try handling problems in code. You could also write things to error, which actually delivers it to prompt. So you could actually do, the regular code trick of if something bad happens, write to error, and it actually shows you up on your prompt. Node could also run on memory. This is one reason why you usually try to write memory efficient code. So if you have variables that not really needed anymore, just remove them and do garbage collection of it, and so that it could still keep on going and don't have to worry too much about RAM. If after 10 minutes, if a task doesn't really update anything, so it doesn't do anything, like it has counters. If it doesn't increase a counter or write to memory or write to error, if it just basically doesn't know what's happening for the last 10 minutes, it just basically kills the job and tries rerunning the task again. So basically what you want to do is always make sure that there's regular updates. So basically make sure that, okay, something's being happening. So if you're doing a process that's going to take really computational intensive, occasionally write to error. Like just saying, okay, everything's still working fine. That way it writes error, goes through the system, and the clock is reset again, so you don't have to worry as much. This is really helpful for Monte Carlo simulations on Hadoop. So like if you're doing Monte Carlo simulation, like if Monte Carlo simulation could take like 30 minutes or 40 minutes on one map job. Like at times, like nothing's happening. That it just processing along, doing actual work, but it's not updating anything. If it's not updating anything, then Duke doesn't think that it's actually working anything, and kills the job, well, kills the task. And so if you're doing a really computational intensive one, make sure you either write error or update some counter. If node fails, then Hadoop tries isolating a node from the system, so then reassigning the tasks to other nodes. So it just basically tries isolating everything down and basically gives a red flag to the administrator to say, okay, check out this node, see what's going wrong. Main node failing, this is really problematic. If it fails, the whole system is down, or at least a portion of it. Then recovers by reading information from the secondary main node and edit logs, and tries to basically piece together how the file system is arranged so that it can go along its way again. Unfortunately, even if a main node does go down, there is still some error, some data loss, so prepare for that. One of the problems is too much memory. You have, too many files on memory, so if it's highly recommended to keep most of your data onto a single job or something similar. So be careful of putting tons of little tiny files inside. With the Hadoop, it could take 30 minutes for a new main node to be set up. Hadoop 2 takes a minute or two. So let's go, there's basically several different ways of running Mapreduce jobs on Hadoop. Java, which basically everything's written in Java. You also have a lot more options there because you have you can actually create your own counters and do crazy shit. You could also run Hadoop streaming jobs, which is C++. You pretty much almost any kind of language, C++, Python, R, whichever you want. This is usually easiest and but least efficient interface. But even so, it's like the easiest one to work with. And Hadoop pipes. This basically connects C++ to Java. So this is almost as efficient as running Java jobs. Yeah, this is basically how, in the command line, how you can run a Java job. Basically have Hadoop, jar, and Java file, and then put the various arguments that you want onto it. Hadoop streaming, you have to tell a little more information. So it's actually still a Hadoop jar, but you actually tell it where the Hadoop streaming file is, and then basically where your input is, what's your input, what's your output, directories, and like where your files are for your map function, your reduce function. Oh yeah, I was thinking of printing off a cheat sheet, but I forgot to do that. But I had one made up, but I forgot to print. I can give one later on if you want, but that details like a lot of the stuff here. Yeah. Hadoop stream for Hadoop streaming. Hadoop 1 can only do can only process text, so it basically has to take in text, then output. The map function has to output text, so print to run a standard output, then takes that standard input, puts back into the reducer function. Oh, what the hell? Oh. Oh, okay. Okay, sorry, back again. Yeah, I could also do, but Hadoop 2.0 could do streaming objects as well as text. Usually have to do slightly different. Like for Python, you use the bit function instead of printing. Sorry. Oh yeah, for 1.0, you basically separate the key value pairs by a tab. But 2, you basically to emit jobs, you basically have to use a special function. Python's emit for one package of R, there's this key value pair, and does it like that. For Hadoop pipes, it's also Python as well. Uses C++ pipes operator, so connects Java to C++. So for jobs, you can actually like view the process of the job by this here, this information here. So it gives you all the details of what's happening. This is all my own little pseudo distribution cluster on my laptop there. So, and this also gives you more information of like how things are going, what applications are running, what's happening. So like what users, there's nothing happening right now, so nothing on there. There's various different commands for Hadoop. I mostly use HDFS, but so DFS, but there's various functions like taking files taking blocks from Hadoop to check things out. There's jobs, pipes, etc. There's also yarn commands to basically do jobs, and various administrative commands too. So like regular ones, say for HDFS, say HDFS, I want to list off the files in certain sort of directory. HDFS, DFS, dash LS, and the directory you want to look into. Same thing, you can do cat. So if you know bash, this would be really helpful because the commands are very similar, except for like put, which actually takes something from a local file system onto Hadoop, and same thing with get, it does the opposite with get. You can also merge files, HDF files to a local system with get merge. So for instance, if I do HDFS, DFS, LS, yeah, it's hard to read from there, unfortunately, but it shows off like what directories I have in there right now, which is input and output. So if I make a file with hello world inside of it, if I put it in and onto Hadoop, onto my files, see it brings it up there and it says one's there. Then when I do the ls command, it actually has that example.txt there. Catenate, so cat is basically read off the file and put the screen. So as you can see down here, hello world, what we had in there earlier. I didn't want to print off a whole big text file, so. You can also remove files. And as you can see, one thing deleted. Yeah, so does it pretty quickly. Hadoop streaming command. So this basically, if you want to do in text file in command prompt, this is basically how you oriented it. You have to tell where your input file directory is, output, where the mapper execute is, where the reducer is, and so on, and basically tell other information like what combiner is, if you have a combiner, and what it is, and directory where it is, the input file format, output format, and reduce number of reduced tasks you want onto it. You could this is how you do specify the number of reduced tasks. You can also like define some properties which inside of your command. So this basically how to configure your Mapreduce job. Yeah, I'm getting pretty close to the actual R code that you run as Mapreduce. It's very highly configurable, so most software's for tuning though, but there's some interesting ones there too, but it's too big for me to get into. If you want to, for debugging, you have to go, there's 3 different ways of having Hadoop. Local mode, which is basically just the single machine, and there's only one single JVM instance. In pseudo distribution mode, there's usually essentially is a one cluster node with running various different tasks. And there's also full distribution mode, which basically is a cluster. There's various different counters. Basically tells you how many map jobs there are, how many reducers, how many files go through this system. So this is basically this is basically the logs of the system to figure out what's happening if something's going wrong. So these are various different ones. I'm just going to breeze through them. So like Mapreduce tasks, job tasks, where input records are, like number of records taken in, taken out, how many combined records it put in, various bytes read, bytes read, how many the file that's written to written from the reducers to the HTTPS, like the total number of launch jobs, Uber tasks, everything. Now let's go into actually Hadoop right here. First, before you set up, you actually have to run code. You have to basically set some parameters, like where Hadoop is. like what's the command for running Hadoop, and what's the command for streaming Hadoop. These are basically tells you where on the system each file is located, because it needs to know that to run the jobs. Or you can also have this all up in a bash file so that it's in your file system. So Mapreduce basically helps define the Mapreduce job. So the input could be like a set of file paths, or even a big data object, which is like stub data. Like just basically tells you where in the directory structure where all the data is. Or it could be a combination of both. Output is a path to the destination fast. If it's missing, then a big data object is created and sent back. So this basically just tells you where it is in the data. When the data is according to a variable. For the output, you have Hadoop does not like overriding things, because you can potentially waste really valuable data that way. So if you're writing to a directory that already exists, you have to remove that directory first, then you can write to that directory. Map basically tells you it's our function, which basically returns null or a key value pair. Reduce is also another optional R function that either returns a null or a key value pair. Combine does something very similar, but the combined variable is either to be true if you want to use the reduce function as the combiner, null if you want to use no combiners at all, or you can even specify your own combiner. Input format basically tells you how the data is structured. So native is our data structured, like our data type. Could also be text or JSON file, CVS, separate value file, or pig or Hive. Output format is basically how you want your data to be outputted as. So it has very much like similar data structures. Key val basically function returns a key value pair from when you're writing it out. Only val could ever be null. You don't want key to be null, because what is that? You can't do a hash function on a null value. So from DFS basically reads off a file from DFS from your Hadoop file system and brings it into our program. And 2DFS is basically for project purposes, for test purposes only, where you're taking your data that's already in your computer, putting onto your file system for testing things out. So keys and values. So if you want to just get the keys from a key value pair, then you basically use the keys function. If you want to get the values, same thing, but we use values instead. And as you remember before, we had a primer, a preamble, basically specifies like what the prefix is, what's the where the Hadoop streaming file is. So in MRR, this uses, by the way, the package RMR2, which is a project that's run by Revolution R, which is also open source as well, so it's considered one of the better ones. But R.options give you various different options to try out. So so this is basically how you put things in the background. You could even put it into local mode to basically do some debugging to figure out what's happening wrong with your code. You also backend parameters basically let you specify various different parameters you want to specify for the job to help optimize the job. Yeah, so backend, as I said, it's either local or Hadoop, which is basically the Hadoop, where Hadoop is, if it's Hadoop, then the stream is right to the cluster or pseudo cluster, and performs the job. Profile nodes basically tells you how you want to collect your data, and like this for just debugging it. So this basically like collects all the information from various different nodes to basically figure out what's happening. So let's go to a word example, word count. So we do our preamble first, then bring up the library RMR, and like the data table instead of the data frame. I'm first going to remove this this directory here because I run a couple times to check things out, so I don't want it to keep on deleting manually and put it back in. But then this here, then basically this defines my map function, which basically takes in the first K is the number of bytes it is from the start of the file, and lines is the actual lines of the file. So it first separates the words by the space, then for each one takes out that list and lists them, and for each one puts a key value pair of 1 and of the word and 1. And reduce function just basically does a summation of all your counts for each word, and specify my output, war and peace, well, input, war and peace, output, my output directory, specify format, what my map function is, what my reducer function is. Believe this, the combiner is by default is true, but yeah, and this basically outputs that job to that directory. Then I basically, from that directory, I take it from there and put up a direct count, and put that count as a data frame. Then basically, I've set the column names to be to word and count, and if I arrange them by range them up, so the word that's used most often is the word the, second and thirds to, and since, and you can tell where I got this file from by the end of the file. So linear regression, let's assume for now that the number of parameters you actually that you want to go into is actually enough to fit onto memory. So basically from linear regression, we know this is true. So what we do here is from this we know that these data structures, these matrices, are small enough just to fit in memory. So all we need to do is to get this to get our beta value, beta hat, is the matrix X transpose X and X transpose Y to get our beta value. Yeah. To break up this calculation, we need to break up our matrix X into sub-matrices. So, for instance, X and Y, and this X1, 1. Remember, this is all done up by file size, so these are in the same file basically, but from there basically you can tell like if it's arranged by structure by file size, like every record gives you all the information for one row. And from here, X transpose X, we could basically just get up from our partition. Or first partition, X transpose X. Second partition is X transpose X. So on. So same thing with X transpose Y. And notice that it's all commutative, so it doesn't really matter which ones operate first. So like X transpose x1 transpose y1 plus the very end xn transpose yn is the same thing as the other ones. This makes it up so that it runs so you can parallelize the tasks. It doesn't matter what order it is. So if we run the code, there's just basically do a setup, number of parameters 10, where beta true is from 1 to 10, and what should I think, 1 to 11, and we basically have our cbind making up our files, and I'm just basically putting a file onto a system. And just to make sure that you guys know this is happening, that it's not just using the data inside, I removed those variables, and then define the map function. So, our partition file, we don't really care about the key here, so it's just a dot. But we want xi, which is our partition. So we have xi equals xi, get rid of our last value, which is that, which is the y value, and we basically get a transpose of x transpose of that, and same thing with the y value. So we just basically retrieve it with y values, just the y values, and one without the y values. Get the x transpose y there, and when we sum it all up, we use the exact same function for both of them. So, and basically from here we have two Mapreduce jobs, and we take the value from that. The values that here basically I put a list in because that way. When each one's appended to the other, it doesn't append it to a matrix, so it makes it a huge long sum of matrices, which it thinks if you do a sum of that, it just sums up every single entry along that, the whole system. So list basically makes it so that you actually adding up matrices, not just individual elements of it. And because of that, it returns a list, so you just want the first item. So we basically do up all the functions here, and then we just basically get it up, and then from there we have our x transpose x, our x transpose y, and then we'll just solve it. And if we find it here, it's pretty damn close. Second one, last topic is your data isn't that big. You could also, there's many difficulties and limitations to Hadoop, which means that if you can work with SQL, it's better to work with SQL. First of all, it's like you have to basically do a paradigm shift of Mapreduce. Basically, you would have to re-envision the algorithm instead of having what is already set. So debugging is a lot more harder because you have to keep track of very different nodes. Data security isn't as well defined as most SQL engines, so you have much more security with your data on SQL. But one of the main problems that people think, okay, I can't fit everything into memory. So how do I fix that? Well, gigabytes, first of all, the gigabytes CSV could usually be loaded into memories on most computers very easily. You could also process the data, reading line by line. If you could do that, usually that's a better job. It's easy to code up, write it up. You don't have to worry too much about debugging or anything on Mapreduce, on Hadoop. So R and Python have functions like read lines, which read a file line by line. SQL could handle a lot of information calculations. SQL doesn't require all the data to be loaded into memory to execute queries, so it could handle data over massive gigabytes, which you also could index too. so you could actually quickly reference things and quickly calculate things up. There's also R packages like dplyr, which can translate R code into SQL queries and execute those that code onto the back end. So just like you take a stub of data from a table, put that in, and you could basically do a SQL queries right in R without really needing to know much of SQL. And PostgreSQL has a nice package called extension called MATLib, which allows machine learning algorithms over large data sets in Postgres. So that's a really nice thing. If the data isn't structured for SQL, like JSON files, well, first of all, Postgres does have a JSON data type, so you can actually have that stored as a data type inside of your table, and do processing on that. You can also process the file using a script, reading line by line, and that's it. Oh yeah.
I mean, these data types of Postgres, I mean, you can't query using JSON. I mean, like through the JSON, whatever, like a part of the JSON blob you want. So it's like essentially it's just a blob, not really like a MongoDB JSON.
Well, I haven't read it as much as I should on Postgres, but I do believe you can do some checking like that. If nothing else, I could also show you how a query looks like when it's running. So, okay, let's run this. This is linear regression. As you can see, it's loading it up. It's it's not as fast as what it would be like for SQL, and mind you, this is only for a single data node. It takes a little longer than I thought. Yeah. Well, that's going on. Any other questions? Yeah.
I read that, because like Hadoop is kind of like more like a batch style old way of doing things, whereas
Yeah.
Google itself and others are moving to more like a stream, like basically like a Spark streaming or like Storm.
Spark streaming is actually more of mini batch. It's still a batch process. Believe there's like streaming format, was it Storm or something, I think, which can do very much like stream, but Spark could like mini batch is pretty good too. So, and I believe Spark is more evolved right now. Yes.
So how do you implement the map and reduce functions for linear regression? How does the algorithm work?
Basically partitions everything up. You have to basically think of along the lines of, okay, partition the data up into various different parts. And so, you know, what I was saying before, partition the data up to parts where it's, you could easily commute them by some operation. So like plus or addition or multiplication, so that it does it all up in that process. It's sort of like recursion in a way. It's just having to get through that mindset. As you can see, it's actually running now. And earlier it showed, you know, like various different information here, various counters. It's like number of import jobs, input records, et cetera, how many bytes of various different ones. And I think that's the second Mapreduce that's going through right now.
So does it calculate the linear regression of like basically X set of data points?
Yeah, sets it up for one set of point, like the X transpose X for one set of data points, and sets them, calculates up X transpose Y for another set of data points. Like, so
Oh.
it does those thing of it just doing little bits of partition the data out, do a little calculation here, get result, and store it for later on for the reducer. Same thing with each little partition. Then the reducer basically combines everything up together, and you basically send up the last little bit of it to memory, and from there you could actually just do a solve for X transpose X beta hat is equal to X transpose Y. Just solve for that system, which is you could easily do down in memory, in which case it will do it in memory. Like if this was an actual cluster, it would basically send off all the data, it'd do the calculations up, then sends off the X transpose X to the back to us, back to my computer. Damn it, I thought of something and forgot. Yeah, sorry. Yep.
Yeah, you mentioned that SQL is much easier to to read and write and like proc compared to this and all the hassle.
Yeah.
But there are it's sort of like people are interested like Pig and others basically that kind of translate or
Yeah.
do SQL like.
It makes it much more easier to use. However, that still has a bit of problems, but still, you still have the process of like something failing, something happening wrong here. Yeah, so it isn't as consistent, but it's a lot easier to program. Like instead of like a whole couple days working on a Mapreduce job, you could probably 10 minutes.
Active program.
Yeah, like that's for writing up on pigs. Like instead of doing several different Mapreduce jobs, like just write up in pig for like probably 10 minutes or so. Okay, that works, and do it up, send it off, it works. But yeah.
Wait, so beta hat is the slope of the linear regression?
Yeah.
But then why is that why does X transpose X times beta hat equals X transpose Y?
No, X transpose X transpose X beta
Yeah.
hat equals X transpose Y. That's how the calculations are for usually you find your beta hat by finding the inverse of X transpose X times X transpose Y. That's usually your beta hat. But instead of doing that whole calculation up with one go, you break it up into this matrix and this matrix, so you don't have to inverse a huge matrix in Mapreduce.
Or do you have to calculate the average and then subtract each value?
No.
So just a formula,
Yeah.
X transpose X inverse, X transpose Y is beta hat. That's the least square solution. Yeah,
Oh, so it's like
he's
this-
basically trying to calculate that by splitting or partitioning the matrix.
Yeah.
Okay.
Anything else?
Yeah. Yeah, you can see tells you very different information of the job, with the Mapreduce, so that way it helps you figure out, okay, if there's a lot of failed jobs and repeating it several different ways, it could tell you that something's going wrong. So this way it helps you understand, okay, something's happening here. So it helps you track down errors. That's also one reason why you like trying to write to standard error to help find out errors.
So how big the data was here?
Well, it has to be pretty small because my own laptop.
So it's taking so long because you are
Because I have to,
running.
because the overhead of Mapreduce of Hadoop, so it's all running in JVM. So basically, I have to run JVM instances, like several JVM instances, while running our code,
So it does it
So
all.
basically, you're doing on small data set, but that is,
Yeah.
you shouldn't really do it on a small data set, but if you have a very large data set, then.
You
still
kind of need a
yeah,
cluster.
Exactly, you don't need this.
Yeah,
So
if-
because it will be done if you just use X transpose X inverse.
Yeah.
It will be done in a second.
Yeah, exactly. If I actually did up the same code for like an R, just completely
Yeah.
in R, like that's a second, less than a second, it's half a second.
Yeah.
So there's a balancing act there. It's good if you're like have a really large data set, but if you're trying to process like little tiny things, like why? It's slower.
It's not for meant
Yeah.
for small data sets.
Yeah, it's meant for really high output.
Yeah.
Anything else? Yeah, that's it. Please. Yeah, I didn't know how long it takes, so